let me just remind you where we left off. So last time, given a curve, let's say given a curve L, if a parameterization traverses L, let's say x of t, y of t, for t in between some parameter bounds a to b, traverses L exactly once, then the arc length of L is the following. You take your parameters and then you evaluate the integral of its speed. All right, so the speed we saw last time was dx dt squared plus dy dt squared, all square rooted. And this does not depend on your choice of parameterization, so long as your parameterization does traverse L just once. Okay, so we were in the middle of an example last time. So we started off with this parameterization, right? So we have a circle of radius r0 squared, right? So here's your circle in your xy plane. It's centered at 0, 0, the origin, and it has radius r0. And we saw, in our very first lecture, there's nice parameterizations of circles, right? It's basically you parameterize circles by setting x is equal, your radius times cosine of some parameter, and your y to be your radius times sine of some parameter. And then if this were an off-center circle, you might have to add where the center is, right? But you could check your old notes for that. But we know how to parameterize circles. And we also saw, how certain classes of parameters differ, right? So for any constant omega could be positive or negative, just not 0. You could really parameterize a circle, if you want the entire circle, then you could parameterize it with omega t instead of just t. And the only thing you need to be careful of is if you want to parameterize a circle and go around exactly once, then you might have to change the bounds of t according to your choice of omega, right? If omega were 1, then your entire, to go 1 revolution around the circle, you go from 0 radians to 2 pi radians, right? 0 to 360 degrees. If you alter omega, which as we saw last time, omega turns out to correspond to the speed at which you're traveling along the circle, either clockwise or either counterclockwise or clockwise, depending on your sign. So if you alter omega, the speed, then you have to alter what your period is, right? So what your bound on t is. Instead of 0 to 2 pi, you have to divide out by omega, also called the frequency, right? Okay, let's try and, these are all valid parameterizations of the entire circle that go around once, right? So for any omega, these are all parameterizations. Oh, let's call the circle C, all right? Oh, C, oh no, well, I called it L. So L, that traverse L once. Well, you might be finicky and say, well, technically at 0 and at 2 pi omega, you both end at the same point. So technically it traverses once, except for it hits the same point twice. But when I say traverse once, you're allowed to hit the same point twice, just a technicality. If it makes you feel better, you could put a strict inequality here so it doesn't actually go to 2 pi over omega, but and when you evaluate the integral, it doesn't actually make a difference. All right, but hopefully you see intuitively why it traverses once. So let's try and find the arc length. So the length of L is going to be equal to your parameterization, right? So you want your parameterization dx over dt squared plus dy over dt squared, all square rooted, dt, and you want to go from t is equal to 0 to t is equal to 2 pi over omega, right? Because that's where, for any fixed omega, this is what your parameterization, bounds are to traverse your circle exactly once. Now, does someone remember what the integrand here should be? We calculated this last time. So, oh, by the way, I should probably say, so you actually want omega here to be the absolute value, right? For this to hold true, if this were an originally negative omega, then to traverse the circle exactly once, you actually want t to be 2 pi over the absolute value omega. Otherwise, this would be negative, and you actually have t is between something negative, 2 pi over omega, which is negative, and 0. But that's a technicality. So these are your bounds. We know that this is the integral of 2 pi over absolute value omega, and you want to take your speed here to be, well, last time we evaluated this out to be the absolute value omega dt. Now, this does not depend on time at all, right? This is you're integrating a constant, right? For whatever omega was, this is integrating a constant. So you can take the constant out, and you're just integrating 1 over this interval, 0 to 2 pi over absolute value omega. So that's just 2 pi over absolute value omega, and that just gives you 2 pi, which is entirely, oh, sorry. I really screwed this up because this is, last time we did this for the unit circle where R0 is 1. So let me just, maybe I shouldn't have asked that, but dx over dt, in this case, sorry, it's going to be minus omega R0 sine omega t, and dy over dt is equal to plus omega R0 cosine omega t. So thanks for everyone correcting me. Right, I forgot the R0. But these are the correct ones, right? So almost the same as last time, but last time we only calculated this for unit circles, right? So if you just take this, you want to take dx dt, dy dt. So the usual chain rule applies, but there's R0 now in front. So the only thing that changes here is you can now factor out the omega and the R0. So there's an R0 here, but this is still constant, right? None of this depends on t. So there's actually an R0 here as well. And so now you cancel out the omegas, and what do you get? You get 2 pi R0. Now that's actually the perimeter of a circle of radius R, of radius R0. So hopefully people are happier with this. So what you see here, well, you see that this proves, in a very simple case, that the arc length does actually get you, this formula does actually get you what these parameters, ought to, what the length of these curves ought to be. And at least within this very restrictive example of, we've parameterized a circle in many different ways, depending on a choice of omega, it ultimately didn't matter. The omegas canceled out and you were able to get just, a pure, a length of this circle with no reference whatsoever to your specific parameterization. All right. And this is sort of towards this, this comment, how length in general does not depend on your choice of parameterization. As I said last time, this depends on sort of, you want to prove this fact, you sort of consider all possible parameterizations. You use the chain rule, because your different parameterizations are going to have different bounds. Your bounds are going to change, just like how the bounds here change based on your specific parameterization. But it turns out that the way the bounds change, roughly speaking, is exactly the inverse of the way your speed changes, right? You could see that happening here. And because, if you take it, if you trust me, or if you go through the calculations yourself, you can see there's always this sort of analogous cancellation happening. And therefore the specific parameters of your parameterization just never show up in your final calculation of length. All right, so there you go. That's an example of how this formula works. Okay, so let's do a slightly different example, which might be a bit more general. Consider the path given to you by the following. This is x is equal to t squared, and y is equal to t cubed minus 3t. Similar to what we saw previous. I'm going to draw this curve out for you guys because it's very hard for you to get the precise view of this. But the curve here, there is an intersection point or a crossing point at x is equal to 1, or well, maybe not x equals 1, but that part you could probably tell once I draw this. So there's an image of the curve where t goes from minus infinity to plus infinity. All right, and maybe if you write this out, let's factor this out a bit. So this is t times t squared minus 3. So which direction am I traveling here? Let's do a brief refresher of these curves here. Am I traveling like this, or am I traveling from the bottom, looping and then going up? Okay, so in this case, maybe let's look at y. When t gets really, really big, as t goes to infinity, the behavior in y tells you that, well, t squared is going to be very, very positive, right? It's going to be something huge, minus 3, which, the minus 3 is negligible at that point. You're just completely dominated by something huge. And t here is also something very huge and very positive. So this overall thing is going to be very positive as t tends to infinity. The reverse happens, negative infinity. So you're actually going at minus infinity, you're somewhere down here, and then you loop up. So that's the direction of travel given by this parameterization. So now the question is, what is, set up the formula for arc length of the loop. How might we go about this? A lot of this is pretty straightforward, right? You have the formula for arc length. You know exactly in this case what the parameterization is. You don't have to go through the trouble of, I draw a curve for you. You need to figure out the parameterization. You're given it right away. And in this case, you could even, you could right away write down what the integrand is, right? So maybe let's do that. So the integrand, you need to calculate a few things, dx dt. You need to calculate dy dt. And then you got to do some algebra. You need to square it, add them together, square root it, etc. So in this case, you have dx dt is 2t. dy dt is 3t squared minus 3. So this means dx dt squared plus dy dt squared, square root of everything, right, is 2t squared plus 3t squared minus 3, all squared, all square rooted. So what's this? You could, on if this were an exam, for example, you might want to simplify this. Well, you should simplify this or expand this out and simplify. So this is 4t squared plus 9t to the fourth plus 9 minus what is that, like minus 18, right, minus 18t squared, I believe, right? So there's something like 9t to the fourth minus 14t squared plus 9, not mistaken. Okay, and then, you could maybe simplify this further if you want, but let's just leave it at that for now, right? So that's reasonably nice. So the integrand's not too bad, but what are the bounds of a parameterization? So anyone in chat want to suggest a strategy for how we might get the bounds for just one loop of this? Right. So, if you look at what the parameterization is doing, there is, the path it traces out crosses itself at this point, which means that there are two distinct times at which I hit this point, right? If you think of this physically, you have some particle moving down here, and then at time 1, it hits this point, then it keeps on going, and then at time 2, it hits this point again before it goes off and away. So the strategy here is, find T1, T2, where the path crosses, so you want x of T1, y of T1 to be equal to x of T2, y of T2. And you know that where the path crosses, y has to be equal to 0, right? So at intersection, you know that y is equal to 0, which means that by our parameterization here, t cubed minus 3t has to be equal to 0. Or in other words, you have t times t squared minus 3 must be equal to 0. And so what are the times here for y? So we're just looking at the solution to y equals 0. What are the possible solutions for t in this case? Right, so there's 0, and there's square root 3, and what else is there? Right, so there's plus and minus square root 3. However, let's look at what happens at t equals 0. Right, at t equals 0, then 0 squared, x is also at 0. So you're here. And there's no other time at which you're at 0, 0 again, right? So 0, 0, algebraically, on the one hand, you look at the equation for x equals 0, and there's only a single solution to that. That's when t equals 0. So algebraically, there's only a single solution that solves x equals 0, y equals 0, if t is equal to 0. So that can't make sense. Or visually speaking, if you look at this curve, 0, 0 is here. The path doesn't cross itself at time equals 0. So this is not a valid time. Whereas if we take plus root 3 or minus root 3, y is 0 at both t equals plus root 3 and minus root 3. And x is equal to 3, right, at either of those times. So these two are going to be the valid times for your crossing point, right? So looking at equation for x, we see the crossing is at the point xy is equal to 3 and 0 at times t1 is minus root 3, t2 is equal to plus root 3. So this means that the length of your loop is equal to, you're taking the integral of minus root 3 to plus root 3, the square root of 9t to the fourth minus 14t squared plus 9. All right, so that's the setup of your integral. Any questions? Right, so I mean, for a general example so this is in response to a crossing point in a general example. I mean, the point is, if you see any sort of curve, this strategy really relies on the fact that visually you have a sense of what the curve is and where it crosses, all right? And that's why we looked at y first, because it was very easy at this point here to see that y has to be equal to 0 at the crossing point. So you're solving this equals 0 first to find admissible solutions of t. All right, and then once you have that, then you test the points at x of that relevant of the solutions in t for y, and then you could deduce what this is. In general, if you don't have a picture, then you're going to have to solve this in essence blind, right? You know exactly that t1 and t2 have to satisfy at your crossing point. It has to satisfy, the fact that at t1 and t2, x and y are both the same. So you're going to have to creatively figure out, if you didn't have this picture here, you would have to say, okay, let's look at a point in x for which there are two admissible, t1 and t2, such that they give the same. Well, it just has to be plus, it has to be pairs of plus and minus square root of any constant. So that doesn't really help you. You'll have to also combine the fact of yt, to solve these solutions where y is going to be the same for any two pairs. So in general, it's, you'll have to use some ingenuity. In general, this is a very hard problem, right? So the ones you see in exercises and homeworks and tests and exams, it'll have to be somewhat feasible to do, right? So in general, you'll either be given this to help you out, or there's gonna be some stupid, some more straightforward system where it's possible to just solve algebraic for 2 times. And it depends on the integral for calculations. This I wouldn't expect you to calculate on an exam. The setup's good enough. Okay, let's move on to something relatively different now. So we looked at examples of paths and how to parameterize paths in 2 dimensions. Let's now take a look at different coordinate systems you could put on in 2 dimensions. All right, so polar coordinates on the plane. So let's try and figure out what coordinates are, roughly speaking. So, right, so we're very familiar with the sort of Cartesian coordinate system, right? So we draw everything in terms of an XY plane. For each point, we can assign specific values, right? So there's nothing special about the Cartesian plane to assign what points are. As maybe an example, let me draw 2 identical squares, and I want you to think of these as maps, right? So imagine these are 2 sheets of paper. You have their 2 different maps, let's say, of the local area of Toronto, right? So, or even the globe. Let's say here's Toronto. So let's say there are many ways for you to map things out, right? So if you've ever seen like a world map, because our world is round, right, there's projection issues and things get distorted differently, right? So there's, depending on what sort of world map you are, the continents have slightly different shapes. You could print out world maps on like a, maybe by like a 10 by 10 sheet of paper or something. And on any 2 10 by 10, you have 2 10 by 10 pieces of paper, but you have 2 world maps that use different types of projections. That means that, the shapes of the continents are slightly different. And you print it on the same size sheet of paper, and the location of Toronto is going to be slightly different in both of these maps. So on one map, you might have Toronto indicated here, and on another map, you might have Toronto indicated slightly differently. Maybe it's a bit distorted. So maybe in this map, you have a Toronto at a slightly different location. Maybe I'll make it more obvious. Maybe Toronto's here. All right, so I could call this I could describe Toronto in sort of two different sets of coordinates in essence. I have map 1 here, map 2. Toronto itself hasn't changed, right? The location of the city in physical space has not changed. It's, we can't move Toronto around. But it's, Toronto is where it is. But because of these two different maps, we actually have slightly two different coordinates on them, right? For example, if looking at this map, I just have, I'll call this dimension X and I call this dimension Y, then Toronto might have, like if I have, let's say if this is in fact some sort of sheet of paper, I can measure this length dimension in centimeters, this length dimension in centimeters. And maybe in this sort of map, the point has coordinates X, Y is 0, like 3, 4 or something. In this case, in map 2, the physical dimensions of my sheet of paper haven't changed the way I drew this out. But the projection of my map has kind of changed, right? The location of Toronto on my sheet of paper has actually changed, even though they both represent the same thing. So even if I can, I have the exact same ruler here, with the same, in this case, even the same dimensions in centimeters, for example. I could also call this I'll call this dimension X tilde, Y tilde. Toronto in this projection now has coordinates given to me by maybe 2, 5, right? 2 centimeters in the X tilde direction now, and Y tilde centimeters in the 5 centimeters in the Y tilde direction. So fundamentally, what are coordinates? It's you're assigning pairs of numbers uniquely to any single point on R2. All right. So coordinates assign to each point in R2 a unique pair of numbers, which are called the coordinates. So what doesn't qualify as a coordinate system is if, Toronto and this coordinate system, which I call XY. So in this map, it doesn't do me any good if Toronto is represented by, 3, 4, and also 5, 6 in this map, right? Because then I have two coordinates for the exact same point, which isn't very nice because I can no longer tell you uniquely where Toronto is in terms of map 1. So long as you have pairs of identifiers that, where each point in R2 in the real world is given a unique pair, then those are valid coordinate systems. All right, so this is sort of how you should think of coordinate systems. I can change coordinate systems, which is kind of like changing what map I'm looking on. But changing coordinate systems and representing points in different coordinate systems doesn't fundamentally change where the object is, right? The object Toronto, the city Toronto, does not change in the physical real world, but I can vary how I describe Toronto in terms of different coordinate systems. So I want to keep this in mind as as we go into the next section on polar coordinates, which is a different idea of describing points in R2. So this is R2, and we have our classic XY plane. All right, and I have now a point P. All right, this could be Toronto now, but I'm calling Toronto P. And classically speaking, P is described as follows. There is going to be X naught and Y naught coordinates in the XY coordinate system, where in Cartesian coordinates, P is given by X, Y, pair XY is equal to X naught, Y naught, or for any pair. So it could be 1, 2, or whatever, right? So this is something we're very familiar with, hopefully. Now, I should also specify that, this describes that in our coordinate system, Cartesian coordinates, X can take any values in R, Y can take any values in R, right? From minus infinity to positive infinity. Every single point, no matter how far away I am on the plane, I can give you a unique designation, right? What Cartesian coordinates are. So let's now look at a different coordinate system. So here's my old point P. It was described in Cartesian coordinates. But now I can also describe P a different way. All right, what I'm going to do is I'm going to draw a ray from the origin here, pointing towards my P here, right? So X naught, Y naught was my old description of the point P, but I don't even have to reference X naught or Y naught if I don't want to. I could just point with the pointer, say over here, and as long as I have an origin here, I'm going to make a straight line from the origin and connect it to my point P on the plane. And there are a few quantities I could associate with this. I could associate with this a length. I'll call this length R. And I will also assign to this an angle. I'll call this angle that this red line makes theta with a positive x-axis. All right, so R measures the length of the radial arm pointing from the origin. So I'll point out that your textbook and web design calls the origin the pole in these polar coordinates. I don't think this is very standard, but in case it comes to the web design, just know that they use the word pole for the origin. So R measures the distance from the origin to your point, and theta measures the angle in radians the radial arm makes with the positive x-axis. So in polar coordinates, this exact point here is now going to be described by a pair. P is given to you by R and theta. And I'm going to put a restriction on R and theta, where standard polar coordinates, R is going to be restricted to be greater than or equal to 0. And theta is going to be in an interval of 2 pi. All right, it's going to be between 0 and 2 pi, or oftentimes minus pi and pi. All right, so just like in Cartesian coordinates, x is between minus infinity and infinity, and y is taken between minus infinity and infinity. And I claim that you can assign uniquely, a pair of coordinates like that for every single point in the plane. I assert that if you either take r to be non-negative and theta between 0 and 2 pi, or r to be non-negative and theta between minus pi and pi, or in fact, r is non-negative and theta is any 2 pi or 360-degree interval, I'm able to assign to you every single point in the plane. I can get you a pair r and theta that uniquely identifies it. Yeah, let's do some examples of how we're going to assign these points. So if you remember, theta equals 0. So let me draw first several pictures of this, right? So let's say, I'll look at r is greater than or equal to 0 and theta is equal to 0. What ray does that give me? Is this the x-axis, the y-axis, part of the y-axis, part of the x-axis? Is it a straight line? Is it a circle? So the set of points with r is greater than or equal to 0 and theta is equal to 0. Well, if you make an angle theta is equal to 0, you're making an angle of 0 degrees or 0 radians with the positive x-axis. So you're lying actually entirely on the positive x-axis here. Maybe I don't do that quite yet. Let's do r is greater than 0. Theta is equal to pi over 4. What does pi over 4 give you? So not quite. So pi over 4 is 45 degrees, right? So let's see. Well, because everyone wants the y-axis so badly, let's do that in between. How about that? So if I do pi over 2, then indeed you're making a right angle. So this is a ray that is given to you by r is greater than or equal to 0 and theta is equal to pi over 2. Right, that's 90 degrees here. 90 degrees is pi, oh my God. Okay, so 90 degrees is pi over 2. So let's go back to what I had before. Do pi over 4, should that be? Right, so it's 45 degrees line. So this is what that corresponds to. And now let's see, let's find a somewhat different example. Let's do, how might I describe this orange line here? So typically speaking, for conventional polar coordinates, I know, by the way, your textbook does this slightly differently. I'll get into that in a moment. But for now, let's always restrict. I'm going to make a general rule because this is how math generally works. R is going to be always restricted to be non-negative, all right, unless otherwise specified. I'll give you the exceptions later. But if R is always going to be taken to be non-negative, and I want to describe this orange ray, what should I put theta here? right? So I could write this to be theta is equal to positive pi, or what's the other option here that I have? So if theta is between 0 and 2 pi, and I claim that could take, visually speaking, this could be either, I could describe this angle here as positive pi, right, which is in degrees, right? That's going to be 180 degrees. Or equivalently, I could also describe this as minus pi, which is minus 180 degrees as measured with the positive x-axis, right? So if I choose this range here, I could also equally describe this as theta is equal to minus pi, all right? So I know, it's kind of weird, right? This illustrates two things. This is why we need to restrict the angles of theta to 2 pi intervals, because, at some point you're going to go all the way around the circle. And that's not going to, you're going to get back to where you started when you make a 360-degree or 2 pi revolution. So you want to stop double counting things, right? So this is why there's this technicality of restricting what theta is. Now, oftentimes in polar coordinates, they're not going to give you explicitly what these bounds are. What's going to happen usually when we use polar coordinates is these bounds are important when you end up setting up integrals in 2 dimensions, all right? You end up, if I have a subset of the entire plane, let's say I have like a circle, an off-centered circle in one of the quadrants, or if I just want to describe the quadrants, then I need to fix a range of theta, all right? So if I say describe the right half of this plane, then I could describe this as the entire region R is greater than or equal to 0. And I could give this right half as theta is between minus pi over 2 and pi over 2, which is minus 90 degrees and 90 degrees. And that's a bit easier, that's a bit easier to describe than if I described it using this formulation, right? Because in this formulation, if I want to describe that right half plane, then this corresponds to theta between here and here, which is going to be in this, if I restrict my domain here, that's going to be between, 3 pi over 2 and 2 pi, and also theta between 0 and pi over 2. So I sort of have to, if I want to describe theta in a continuous interval, I can't really do that if I restrict myself to this 2 pi interval. Whereas if I restrict myself to this 2 pi interval, it's very readily described by minus pi over 2 to pi over 2. All right, so that's why we tend to restrict intervals here. And yes, the convention here is theta equals 0 is always going to be the positive x-axis. All right, every single one of these angles is going to be taken to be respect to the positive x-axis. And so minus pi and positive pi gets you back to the same place. All right, it's just when you want to restrict what your map looks like, what your available coordinates are, it tends to happen that theta has to be restricted between 2 pi intervals, just so you don't end up double counting things. That's just a general rule with these coordinate systems. We'll do a lot more practice starting out. There is, by the way, a lie here. I told you it's very important not to double count things, but at the pole here, you actually are double counting a lot, right? At the pole here, you're a distance 0 away from the origin. So technically there is no angle, right? If you're at the origin here, you're gonna have any possible and every single possible angle is really technically a valid description for what your origin is. So a convention dictates that the pole or the origin is R is equal to 0. All right, and there's no angle designation to what this point is. Okay, so let me go ahead and do the following. Let's now look at constant R. Okay, so let's say there's no restriction on theta. Let's just say R is equal to 1. What geometric shape is this? After we do this, we'll take a brief break. So what is R equals 1? Right, so this is a radius 1 circle because this measures every single possible. If I measure let's say 1 here, then if I don't restrict theta at all, let's say theta is between 0 and 2 pi, then I just get every single possible R, the point that is distance 1 away from the origin, which gets me this full circle here. All right, so that's 1. Now, what is R is equal to 2 and theta is between, let's say, 0 and pi over, well, let's say pi over 2. So this should be a portion of a quarter of a circle of radius 2, but it's only a quarter of it. Exactly. So this is going to be at 2 and at 2. It's only going to be a quarter of the circle up to, from angle 0 up until angle 90 degrees. And similarly, if I have, let's say, r is equal to 3, and theta is between minus pi over 2 and positive pi over 2. Actually, let's make it a bit less redundant. Let's say theta is between minus pi and 0. Well, then this is going to give me the semicircle. Let me get you the conversions, all right? So how to convert from polar to Cartesian, all right? So let me draw another picture, lots of pictures here. I could have used someone before, but I forgot. So here's P. And in Cartesian coordinates, as coordinates y0, or x0, y0. All right, so that's what P is. Let's make this a bit bigger. All right, now I could do some basic trig. So let me draw my radial arm here. So my radial arm R, so this is also R and theta. My radial arm R is hypotenuse of a certain right angle triangle, right? There's a right angle triangle I could draw here. And I could figure out what x naught and y naught are based on this, right? X naught is going to be equal to the hypotenuse of this triangle times cosine of my angle theta, right? Remember, for a given angle theta, your cosine of the angle is the length of the adjacent leg over the hypotenuse. Now, the length of this adjacent leg is precisely x naught, and the hypotenuse is r, right? So cosine of theta is precisely x naught over r. And now if I multiply that by r, I just get x naught back. So I have that x naught here, whatever this is precisely r cosine theta. And as well, I have the fact that this leg of this right triangle here is given to you by r sine theta for the exact same reasons, except now you want the sine of the angle opposite over hypotenuse. All right, so this comes from trig. And so from this, we get the conversion formula for from r theta. So if you're given a point in polar coordinates, and you want the corresponding xy coordinate, then the formula is as follows. You want your x value is going to be given to you by r times the cosine of your angle, and y is going to be given to you by r times sine the angle. All right, that's exactly that comes from this the trigonometric diagram we have here. And now what's x, y to r theta? Well, you could find r relatively easily. So you want r squared to satisfy what in this case? So if r is the hypotenuse of a triangle, what does r squared satisfy? So this should be, by Pythagoras, it should be the length of this leg squared and the length of this leg squared all added together, right? So this is x squared plus y squared. So if you using standard polar coordinates, r must be positive. This is the positive square root of x squared plus y squared. And what about theta? Well, you want the tangent of theta is equal to the tangent of this angle here. Well, the tangent is opposite over adjacent, right? Now, opposite, this leg is y0 or just y, and this leg is x, right? So this is going to be y over x. So this means theta is equal to arctan y over x, or the inverse tangent of y over x, right? So now here you see the indeterminacy in theta, right? As you know, the tan obeys some sort of pi periodicity, right? So for every given, for every single number you put in here, your calculator, I think it restricts theta between minus pi and pi, I believe. So it's going to give you some angle between minus pi and pi. But you could transfer this angle, you add, it's true if you add multiples of 2 pi or whatever. So really, theta here it depends on which theta here you want to choose. This is not uniquely determined, right? you could either have theta, like we said earlier, if you're lying here, you could either describe that as theta. A point here is either theta as minus pi, or theta as plus pi, or you could also do theta plus theta is 3 pi, etc. Those are all equivalent descriptions of that point. But if you restrict, for technical reasons, you decide to restrict, you could also find within any 2 pi interval, there's a unique theta that describes a given point. All right, so that's the technical point of this restriction business. But this is how your conversion works. Right, so let me find some examples for you guys to do. Let's do convert xy is equal to r theta for the following points. All right, so the first one, xy is equal to 3 minus 3. 2, let's do the point xy is equal to, let's say, 1 and root 3. So let's say that's part A. And part B, let's do convert r theta to xy for the following. Let's do r theta is equal to 4 and pi over 3. And 2, let's do r theta is equal to 7, 3 pi over 2. Let me give you a couple of moments to try this yourself, and we'll go over this together. All right, so let's take a moment to go through this. Actually, because it's simpler, let's try B first. All right, let's do B1. Does someone have, maybe in chat, you could type out what you have for B1. So by the formula, maybe I'll write this down. So x, once again, and y were r cosine theta and r sine theta. And so together, this means that x is going to be equal to, well, r in this case is 4 cosine pi over 3, and y is equal to 4 sine pi over 3. All right, now does someone know what cosine and sine of pi over 3 are? So last time I remembered, someone asked a question, which cosine and sine angles should know. So here are the important ones. So the important angles, here are the following. All right, so it's not too many, but these come up again and again and again. So it's worth knowing them. The first one is the angle that's given to you by the angles of the 1, 1, root 2 triangle, right? And these have pi over 4 or openings. Pi over 4 being 45 degrees. So in this case, sine of pi over 4 is equal to cosine of pi over 4. And what's that equal to? Here's someone in chat. Right, it's going to be 1 over root 2. Now, there's another triangle, which is important and relevant to this case. This is a 1, 2, root 3 triangle. This is angles pi over 3, which is 60 degrees, and angle pi over 6, which is 30 degrees. All right, so you have a 90-degree angle here, 90 degrees, 60 degrees, 30 degrees. And so reading off this triangle, you have the fact that sine of pi over 3, right, is the same as cosine pi over 6, which is the same thing as root 3 over 2. And then you also have sine of pi over, sine of pi over 6, the same thing as cosine of pi over 3, which is the same thing as a half. So knowing these, you can plug in the above. So cosine of pi over 3 is going to be equal to a half. So this is 2. And then sine of pi over 3 is going to be root 3 over 2. So that's going to be 2 times root 3. All right, so your first point here, whose polar coordinates are given to you before pi over 3, those are given to you in Cartesian coordinates, which are easier to imagine, with points 2 and 2 times root 3. Any questions with how I got these? So maybe I'll draw a diagram here. So previously we have, well, I won't draw the diagram. You could imagine, maybe you could plot this up yourself if you want to see where the point is. But this is basically pretty formulaic, okay? So 2 xy, well, this is r sine 3 pi over 2. So 7 times the, 7 times the cosine 3 pi over 2. And 7 times sine 3 pi over 2. Now, does someone want to simplify this for me? What are x and y? So one thing you should know for this class is the sine, so 3 pi over 2 is, it's a multiple of 90 degrees, degrees, right? It's what, 180 plus 90 degrees. It's 270, whatever, right? So that was incorrect. This is the point being that you know that sine and cos. Maybe something else you should know from previous classes is the graph of sine looks like this. This is sine. This is cos. It's shifted. Right, and you have this is pi over 2, pi, 3 pi over 2, 2 pi. All right, so those are the graphs of sine and cos. Hopefully it's not too bad for you to remember what these values are for multiples of 90 degrees. Okay, so purely algebraically, you could see that cosine of 3 pi over 2, that's going to be 0. And sine of 3 pi over 2 is going to be minus 1. All right, I should probably specify this is 1 minus 1. So that's all the pre-calc you need to know for trig, and a couple identities that we'll get to later. But this is going to be minus 7. There's a somewhat easier way in this case to figure it out, right? If you just read off, even before these formulas, you know, we have our intuition from above, from these pictures here, what exactly these, you know, if you just imagine this is r, this is theta, what am I saying here? Here I'm saying r, the length you are away from the origin is 7, and you're making an angle of 3 pi over 2 with the positive x-axis, right? So along here is 0 degrees, it's 0 radians from the positive x-axis. Here is positive pi over 2 from the x-axis, positive x-axis. This is positive pi away from the positive x-axis. This is positive 3 pi over 2 over the positive x-axis. And that's what my theta is. I'm at 3 pi over 2, so I'm somewhere along here, and I'm at distance 7 along here. Right, so if I'm along here and I'm distance 7 with the origin, then I must be at the coordinate x equals 0, because I'm on the y-axis, and y must be at minus 7. That's what my Cartesian coordinate is in this case. So as you can see, there are cases where, you know, this formula here always works out, but, you know, sometimes if it's easier, the geometric picture is a lot easier, right? Once you know these are in polar coordinates and you know the intuition of, you know, the picture of polar coordinates as being measured by distance with the origin, that's positive, and also an angle that you're making with a positive x-axis, then certain angles are very straightforward to see. You know, I didn't do it here, but if theta were, you know, pi over 4, then you also know that lies along sort of, you know, rays that are 45 degrees. Let's take a look at A. So if x and y are equal to minus 3, 3, or sorry, 3 minus 3, I really screwed that up. You could do this purely algebraically, right? So algebraically, you have the fact that r squared is equal to x squared plus y squared, right? So we are x and y are 3 minus 3 respectively. This is 9 plus 9, 18, which means r is going to be positive root 18. And theta, you could say, is the arctan of y over x, arctan minus 1. All right. And then you need to figure out what arctan of minus 1 is, which is really, you got to figure out what tangent of theta is equal to minus 1. Tangent theta is sine of theta over cosine theta. So you want sine of theta and cosine theta to be equal to minus 1. What you want, so you want sine of theta to be minus cosine of theta, and you want to solve for theta. And now you want to look and see, okay, well, where is sine of theta equal to minus cosine theta? And you look at a chart here. But there's an easier way to do this geometrically. Look at x and y here. You plot your point 3 minus 3. Just 3 minus 3. Here's your point 3 minus 3. And you draw the radial arm from the origin to 3 minus 3. And you label the angle here theta. And geometrically, could someone tell me what this theta is? Right. So this theta is minus pi over 4. Or there are other options for minus pi over 4, right? This could be well, this could be, let's see, 3 pi over 2 plus another pi over 4. Right? That's what, 7 pi over 4, I believe. and they're, they're a periodicity, right? You could write this in many other forms, right? So you could give an expression in terms of any 2 pi multiple of this. But the benefit of the geometric picture is you didn't really have to think of, okay, you bring out a calculator or anything like that to verify what arctan of -1 is. You just drew a picture and say, okay, well, this is making a -45-degree angle with a positive x-axis, or it's making a 7 pi over 4 radian, angle with a positive x-axis. All right. 2, I have xy is equal to 1 root 3. Now you could do this once again algebraically or geometrically. This is 1. This is root 3. You have a point here. So what's the angle here? Well, this is a special triangle, so this is just immediately r theta. Well, r, you could do the usual calculation, or you could realize this is a special triangle. This is the hypotenuse has length 2. And the angle here, this is a 1, 2, root 3 triangle. So this is a 60-degree angle. It's pi over 3. Now, I will mention your textbook goes into quite a bit about calculus on these, how to take derivatives and, finding tangents, the velocities and all that. We're not going to bother with that in this class. All right. So what's covered in this lecture is, and what's assigned the web assigned is what you're responsible for. Let me try and illustrate to you how we might draw polar curves. So these are curves given, well, these are curves in the xy plane given by expressions involving r and theta. All right. So here's an example. Let's say r is equal to 1 minus sine theta. All right. So what r is equal to 1 minus sine theta? Let me do the following schematic, x and y. I'm going to put a table of values here of very common, of easy values of theta and r that it corresponds to. All right. So what this is saying is at a given theta input here, my r is going to be prescribed by the value 1 minus sine theta. In other words, I want the set of points r theta that satisfy this equation, right? So any given theta here, I want to be r away from the origin. I want to be 1 minus sine theta away from the origin. So let's try this, right? So if I'm at theta is equal to 0, what r am I at according to this equation? So I plug in 0 to sine theta and read out r equals 1 minus sine theta. What is that equal to, right? So this is 1. So if I have 1 here at here at theta is equal to 0, I'm at the point r is equal to 1, right? I'm distance 1 away from the origin. Great. Now let's try theta is equal to pi over 2. Now how far away am I at the origin? R equals 1 minus sine pi over 2 away from the origin. What's sine pi over 2? Or what's 1 minus sine pi over 2? Right. So this is 0 away from the origin. So when I look at the, in polar coordinates, when I look at theta is equal to, when theta is equal to pi over 2, I'm all of a sudden, my point corresponding to this is 0 away from the origin. So I'm actually at the pole, or I'm the origin itself. Similarly, I could do the same thing for, let's say, pi. So I'm at sine of pi. So sine of pi is going to be equal to 0 again. So 1 minus 0 is going to be 1. So now I'm at a distance 1 away from the origin and the direction of pi, angle pi. So I'm here and 1 away from the origin. That means I'm at x coordinate minus 1. All right. And then finally, I have, let's say, 3 pi over 2. That's another fairly straightforward one. So here I'm 3 pi over 2. And where am I? Well, now I am at sine of 3 pi over 2 is going to be equal to minus 1. So this is 1 minus minus 1. That's 1 plus 1, 2. I'm a distance 2 away from the origin in this direction. So this is minus 2. I'm now here. Okay, so now 4 points, and you now let's try and find some. There are other basic points we could try. We could also try something like, if I do pi over 4, there's 1 minus 1 over root 2. If I do, let's say 3 pi over 4, sine of that is also going to be 1 over. It's going to be 1 over root 2. So this is 1 over 1 minus root 2, right? So that's roughly, if I look at this is pi over 4, then I'm going to be at not quite 1 away, but 1 minus a little bit away. So going to be here, maybe. And then I have a similar thing here, where this is going to be somewhere similar distance away from the origin. And then let's say I have plus 5 pi over 4 plus 7 pi over 4. This is 1 plus 1 over root 2, 1 plus 1 over root 2. So they're going to be slightly further away here than what 1 was. It's going to be here, maybe, and then maybe here. And if you fill this out, eventually, you're going to get a curve that looks like this. So I start at theta equals 0. I'm out here. And then as theta increases, I decrease my value a little bit until I hit here. And then I keep decreasing. I hit the origin as theta gets swept out to pi over 2. And then as theta gets increased in pi over 2 to this angle here, I could verify this actually goes up a little bit. I now move away from the origin again until I go through this point. And then I go out here until I hit pi. And then at pi, as I increase theta, this is going to become, this minus sine theta becomes a positive number. So I'm going to increase my distance away the origin here, continue increasing until I'm 2 away. And I'm going to decrease a bit and then come back out here. All right, so what that traces out is a curve called the cardioid. And that's a visual representation of what this is in polar coordinates. Yeah, so this is exactly, it's kind of a heart shape. It's a bit more rounded than heart shape, but this is in essence a heart. All right, hence the cardioid name, cardio. So as you can see, here's the moral of the story, right? This is completely insane to do by hand. However, so you can't expect I can't expect you to draw out polar curves in exam settings, right? It takes forever. But what you could see is from this equation in a polar curve, you could rule out what polar curves this cannot be, right? For example, I could have drawn, if I had a sideways heart instead, right? This would be something like this, right? I'll erase this in a moment, but if I drew something like this, this would be 2 here, or minus 2 here, and then I guess 1 and 1 here. This equation cannot possibly refer to this one because at the intersections, at the values that are easily calculated, these intersections don't make sense, right? At pi, you need the intersection to be -1 on the given cardioid, but here this would be -2 on the sideways one. So if I give you a diagram, let's say I give you 4 options in a multiple choice, with different, maybe different polar curves, you can at least rule out ones just based on the intersection properties at these common points. All right, so that's something that would be, conceivably testable that you should be comfortable doing and identifying from an equation here. Sketching out actual polar curves are kind of insane. You can't really do that in general. All right, but that's what computer graphics are for. But this is in essence how some polar curves are. Yeah, so I guess that's the conclusion today. Next week we'll continue on Tuesday. I will mention this. I didn't have a chance with today's lecture, but I will mention that in the sketching of polar curves, sometimes it is then allowed for you to have R to be negative values. In essence, what this means, I'll try and recap this at the start, is sometimes I think maybe on a couple of the web assigns, if you want to identify what the polar curve is, let's say there's some function here at angle theta equals 0. For some reason, let's say this was, R is equal to cosine minus cosine theta. All right, if this were R equals minus cosine theta, then at theta is equal to 0, your minus cosine theta is going to be -1. So that means that along this ray here, R is -1, in which case you have to interpret that appropriately. That means that instead of drawing 1 away in this direction, you want to go 1 away in the opposite direction. All right, so that would be the point -1 would correspond to, if at theta equals 0, R is equal to -1, that would be the Cartesian point -1, 0, because you're going the opposite direction of your ray. So that's the only consideration you'll have for -R values in polar coordinates. It's when you're trying to visualize these polar curves, sometimes you end up plugging these points in and you get -R values for some thetas. And that's the correct interpretation by going off the opposite direction of your theta.